On April 3, 1974, a deep cyclonic system generated vertical wind shear exceeding 60 knots across the Tennessee Valley. Within 8 hours, 148 tornado vortices had formed across 13 states. The synoptic scale energy transfer overwhelmed the structural load calculations embedded in 1970s building codes. Steel transmission towers designed for ice accumulation and moderate wind loads began to shear at the base connections. The regional power grid collapsed in sequence. The residential building codes in the Ohio Valley during the early 1970s were calibrated for wind loads not exceeding 90 miles per hour in 3-second gusts. Commercial structures used steel frame construction with concrete masonry infill, designed primarily for vertical gravity loads rather than lateral wind pressure. The regional electrical transmission infrastructure consisted of steel lattice towers supporting 345 kilovolt lines with tower spacing at approximately 800 feet. These towers were engineered with safety factors based on historical ice storm data and steady-state wind conditions recorded between 1940 and 1965. The emergency communication network relied on hardwired telephone landlines and a limited number of microwave relay towers positioned on elevated terrain. Weather monitoring was conducted through a sparse network of WSR-57 radar installations with significant coverage gaps in rural counties. The meteorological setup began on April 1, 1974, when a deep low-pressure system developed over the Central Plains. By April 3, the 500 millibar jet stream had intensified to 140 knots over the lower Great Lakes, creating extreme vertical wind shear in the warm sector ahead of the surface cold front. Surface dew points exceeded 65 degrees Fahrenheit across Alabama and Tennessee, while mid-level air remained dry and cold. The resulting convective available potential energy surpassed 3,000 joules per kilogram in multiple atmospheric soundings. The vertical wind shear profile, measured at 60 knots in the lowest 6 kilometers, provided rotational support for supercell formation. The synoptic conditions were identified in real time by National Weather Service forecasters, but the spatial resolution of existing radar systems could not resolve individual mesocyclone structures or provide sufficient lead time for municipal-level warnings. The first tornadoes touched down in Illinois and Indiana at approximately 1300 UTC. Within 2 hours, supercell thunderstorms had developed along a 450-mile front stretching from Michigan to Alabama. The WSR-57 radar network, operating at a wavelength of 10 centimeters with maximum range of 230 miles, could not penetrate the dense precipitation cores or discriminate between rain and tornadic rotation. Ground-based observers reported multiple simultaneous tornadoes, but the telephone relay system became overloaded within the first hour of the outbreak. The National Weather Service offices in Louisville and Huntsville issued generalized severe thunderstorm warnings, but lacked the technical capability to specify tornado locations or projected paths. By 1600 UTC, communication between county emergency management offices and state-level coordination centers had degraded as trunk telephone lines experienced cascading failures from lightning strikes and physical tower damage. The outbreak continued for 18 consecutive hours, with peak tornado activity occurring between 16 and 2200 UTC on April 3. The extended duration prevented the restoration of damaged infrastructure during active storm periods. Emergency power generators at hospitals and municipal facilities were designed for short-duration outages lasting 2 to 4 hours, not sustained blackouts exceeding 12 hours. Fuel reserves at isolated generator sites were exhausted by midnight. The compounding effect of simultaneous infrastructure failures across multiple states exceeded the response capacity of regional mutual aid agreements. Fire departments and ambulance services lost radio communication as repeater towers lost commercial power and backup battery systems depleted. The meteorological persistence of the outbreak was driven by continuous regeneration of supercells along the quasi-stationary frontal boundary, with individual storm cells tracking northeast at 55 miles per hour while the overall system remained nearly stationary. The mechanical failure of the electrical transmission system began with the collapse of steel lattice towers subjected to lateral wind loads exceeding design specifications by a factor of 3. F4 and F5 intensity tornadoes generated wind speeds between 207 and 260 miles per hour, producing lateral forces that caused tension member buckling and base connection shear failures. Once a single tower collapsed, the unbalanced tension in the suspended conductor cables triggered progressive collapse of adjacent towers in a cascading sequence. The 345 kilovolt lines serving the industrial corridor between Cincinnati and Huntsville failed completely, removing 4,200 megawatts of transmission capacity from the regional grid. The sudden loss of major transmission paths caused automatic protective relays to trip generating stations offline to prevent equipment damage. By 2000 UTC, the entire Ohio Valley electrical interconnection had separated into isolated islands with no ability to restore synchronized operation until physical repairs could be completed. The collapse of electrical infrastructure eliminated microwave relay communication paths that depended on commercial power. Telephone switching offices lost functionality as battery backup systems sized for 4-hour outages depleted by 2100 UTC. Rural municipalities relying on party line telephone systems experienced total communication isolation as wooden utility poles were snapped and cables severed by debris impact. The existing emergency broadcast system depended on AM radio stations with transmission ranges of 50 to 100 miles, but many stations went offline when their transmission towers sustained structural damage or lost grid power without adequate generator capacity. County sheriffs and emergency coordinators could not verify the extent of damage or coordinate rescue operations across jurisdictional boundaries. The microwave tower network, positioned on ridgetops for line-of-sight propagation, suffered direct hits from tornadoes crossing elevated terrain, fragmenting the regional communication backbone into non-functional segments. Major transportation corridors experienced simultaneous blockage from structural debris and forest blowdowns. Interstate 65 in Alabama was obstructed by debris from destroyed industrial buildings, with sections of roadway covered by steel roofing panels and concrete masonry blocks. Rail lines operated by Louisville and Nashville Railroad sustained damage when freight cars were lifted and deposited onto parallel tracks, creating multi-point obstructions that required heavy crane equipment to clear. The Appalachian redge forests experienced blowdowns along tornado paths up to 1 mile wide, with mature hardwood trees snapped at 4 to 6 feet above ground level. The resulting timber debris fields blocked secondary roads and prevented access by emergency vehicles. Highway departments lacked sufficient heavy equipment to simultaneously clear multiple blocked corridors. The closure of primary north-south transportation routes prevented the movement of utility repair crews and emergency supplies into the affected region for 36 to 48 hours after the outbreak concluded. Damage assessment efforts were constrained by the geographic scale of destruction and the absence of functional aerial reconnaissance capability. Civil air control aircraft based in affected states were grounded by poor visibility and continuing convective activity until April 4. The few operational aircraft that conducted surveys on April 4 could not systematically photograph the entire damage path due to fuel range limitations and the lack of coordinated flight planning with ground-based damage assessment teams. NOAA personnel attempting to conduct ground surveys found roads impassable and could not reach reported tornado touchdown locations. The absence of real-time damage data prevented state emergency management agencies from prioritizing resource allocation or requesting targeted federal assistance. Preliminary damage estimates compiled from fragmented local reports undercounted the actual scope of structural loss by approximately 40% during the first 72 hours, delaying the deployment of adequate federal disaster response resources. The 1974 super outbreak produced 148 confirmed tornadoes across 13 states during the 18-hour period from April 3rd to April 4th. 7 tornadoes were rated F5 on the Fujita scale, with maximum wind speeds estimated between 261 and 318 miles per hour. An additional 23 tornadoes achieved F4 intensity. The total contiguous path length of all tornado tracks exceeded 2,500 miles. Structural damage surveys documented the complete destruction of 9,600 single-family residential buildings and the major damage classification of an additional 27,000 structures. Industrial facilities totaling 14.2 million square feet of floor space sustained damage requiring demolition or complete reconstruction. The agricultural sector reported losses of 890 barns and grain storage facilities. The total fatality count reached 315 across all affected states, with 5,484 individuals requiring hospitalization for traumatic injuries. Economic losses, adjusted for inflation to 1974 values, exceeded $600 million. The National Weather Service conducted post-event analysis using aerial photography and ground damage surveys to reconstruct tornado paths and assign Fujita scale intensity ratings. Dr. Theodore Fujita personally surveyed the Xenia, Ohio damage path and documented the structural failure modes of masonry and wood frame construction subjected to extreme wind loading. The outbreak directly influenced the subsequent development of the NEXRAD Doppler radar network, which began deployment in 1988 and provided velocity data capable of detecting mesocyclone rotation. The Federal Communications Commission initiated rulemaking in 1975 that led to the Emergency Alert System standards, replacing the previous CONELRAD system with digital encoding and automatic station identification. The American Society of Civil Engineers revised wind load provisions in building codes, increasing design wind speeds for the Midwest and Southeast regions. The 1974 super outbreak remains the benchmark event for evaluating tornado outbreak severity and established the empirical basis for modern severe weather warning systems and structural resilience standards.